All right, now we're going to look at our transcendental functions. So those are our exponential and our trigonometric functions. They also include our logarithmic functions. These essentially are the functions that transcend the polynomial functions, which we were looking at in the previous slide. Before we do that, I really want to take a look at these e to the x functions. So recall from last year that if you have e to the 0 power, you have anything to the 0 power, that's going to be 1. So e to the x has a y-intercept at 1, and then as we approach negative infinity, that value is getting closer and closer to 0, so it's asymptotic with my x-axis, and then as it goes to positive infinity, it's getting larger and larger and larger. So this is y equals e to the x. And then sometimes it'll be worthwhile knowing what y equals e to the negative x equals. That is just a reflection over my y-axis. So it has the same y-intercept, and then is asymptotic with the x-axis as x goes to positive infinity, and then it goes up into infinity as x goes to negative infinity. So let's take a look at this function first. We have the limit as x goes to positive infinity, and I think I've said this before, I need to rewrite limits in my own handwriting, and then I'm able to kind of decode them and rewrite them. That might be a good strategy for you if you have a difficult time just looking at it first. So if x is going to positive infinity right here, I'm subbing the infinity in here. 1 divided by infinity is going to be approaching 0. So that value, if we're analyzing a limit, is essentially 0. So we're going to rewrite that as -4 multiplied by e to the 0 power. Well, e to the 0 power, that's right here, my y-axis is 1. So I have -4 multiplied by 1, which is -4. In this next example, we have the limit as x goes to positive infinity of 5e to the negative x. I don't really like analyzing things with a negative x if I can avoid it. So I like to rewrite any of those negative exponents. So I'm going to rewrite this as the limit as x approaches infinity of 5 divided by e to the x. So my e to the x is getting larger and larger and larger and larger because I'm going to positive infinity. So I have 5 divided by a positive infinity, which means I have a really small number divided by an insanely large number. So that's approaching 0. So we would get 0 in that instance. All right, next we're going to look at trig functions. And with our trig functions, we're going to have to try to use a couple different strategies to figure out what's going on. And you kind of really have to think through these. They don't flow through just analytically as well. So for this first example, we have the limit as x approaches a negative infinity. So you need to think about, first of all, what's happening with our sine function as we go to negative infinity. So our sine function, we know, oscillates between -1 and 1. So even though we're going to infinity, that's still oscillating between -1 and 1. So this guy's going back and forth between -1 and 1. This denominator is becoming an insanely large negative number. So we have a number, some number between -1 and 1, it doesn't really matter in this case, divided by an insanely large number. So the sign issue isn't going to make a difference here because we have some small value divided by an insanely large number, which always is approaching 0. And so since 0 doesn't have any polarity, it can neither be negative nor positive, we're good. We can just get 0 here. You could also analyze this one using the squeeze theorem. So you could say that sine of x bounces between 1 and -1. And then we could divide each side by x. And then say, well, we want the limit as x goes to negative infinity of -1 over x, the limit as x goes to negative infinity of sine of x over x, and the limit as x goes to negative infinity of 1 over x. So you'll see again that the sign doesn't make a difference because I have -1 divided by a ridiculously large number, which is just going to be 0, and I have 1 over a ridiculously large negative number, so that's going to be 0. So notice that this is sandwiched between 0 and 0, so we know it's going to have to equal 0. In the next example, I have 1 over infinity. So again, 1 over infinity is like having cosine of 0. So this is -3 multiplied by the cosine of 0. Well, the cosine of 0, so if you look at your unit circle, or you think back to your unit circle, this 0 point right here is 1 comma 0, right? That's when we have 0 degrees. Cosine is my x value, so cosine of 0 degrees is going to be 1. So I have -3 multiplied by 1, which is -3. And this next one, let's look at this original horrible graph of sine that I did. Notice it's oscillating between -1 and 1 all the way through infinity, right? So this limit does not exist because of oscillating behavior, because as we go to infinity, it's jumping back and forth between -1 and 1, and we never really get an idea of where it's going to end, because infinity doesn't end, so we can't say it's positive, we can't say it's negative, we just say it does not exist. For this last example, I'm actually going to show you a graph in Desmos after we look at it. I look at this and I say, well, 5 times infinity is infinity, right? That's just an insanely large number. Cosine of infinity runs into the same issue that sine infinity runs into, where I'm oscillating between -1 and 1. So I'm really right here going back and forth between negative infinity and infinity. I'm just bouncing because I don't know, this is just multiplying it by -1 and 1, -1 times 1. So and every value in between as a result. So this one's going to be that it does not exist because of oscillating behavior. You could, if you get to this point, you think that that's the answer, you can always try to analyze it using the squeeze theorem. It's always a good strategy anytime you have trig functions and you're kind of stuck. We can bounce between -1 and 1, then multiply by 5x on either side. And what we would notice here is that when we go to sub in that negative infinity, we'd be bouncing between negative infinity and positive infinity. So it's not narrowing down between one value like it did over here. So we can see that the squeeze theorem wouldn't work in this instance. Let me show you what that graph looks like. All right, so this is what the function looks like just when we're looking at it from a broad perspective, or from a closed-in perspective with 0 as kind of our center. But as we zoom out, notice that it's just oscillating back and forth. It's actually a pretty cool function between negative infinity and infinity. We can't even see up to the top of where it's oscillating in between. And as a result, obviously, we can't narrow in what a specific value it's going to be approaching as x approaches infinity, because it's simply just oscillating back and forth, back and forth. So this limit would not exist.